So here's the agenda for today. Do we have, I'm sorry, Arnab?
Hey, yeah.
Okay. So now because
do you want to go first, or do you want to go?
I was discussing, can we have Navin? So my thing kind of follows up on Navin's proposal. So is it possible that we interchange the order?
Oh, absolutely. Yes, it is yes, exactly. So the order was made on probably the order in which you submitted. Okay, Navin, are you a co-host?
I am not sure.
Okay, you should be now.
Okay.
I don't know. It's like two. I think we by the time you'll be ready, so probably we should start. And Sarab, I think you wanted to lead the discussion, if I remember well.
Hi, Alex. Can you hear me okay?
Yes, I can.
Awesome. Thank you so much. So I guess we have Navin here, and welcome everybody for our second session of 2023 proposals. And I really appreciate everybody, all of you who have been making all these active contributions. Very inspiring. Over to you, Navin. Are you ready to share your screen?
Yeah, I'm trying to figure that out. Could you guys help me? I'm new to Zoom.
After a pandemic, yeah, that's pretty impressive. I think you should have maybe I can stop sharing. Maybe that helps. I'm not sure. I think you can take it away. This should be at the bottom. At the bottom is like the fourth said share screen. If you don't see it, it's
right
probably
now I see that. I see that. Thank you.
And another additional thing, if you don't mind emailing your slide at the end, I think many of you are Intel, so you probably know Sarab well. So it'll be great to have them as a reference for future discussions. Thank you.
Absolutely. Yeah, we'll do that. Okay.
And right before you start, do we have Michael here or Rama from the operator SIG?
Yeah, I'm here.
Awesome.
Yes, we're both here.
Great. All right.
Okay. Do you guys see a full screen or some sort of split screen? Okay. All right. And I don't know how to do that either. So sorry about that.
You can just go into display settings and then swap.
Okay. Sorry, I'm eating into the presentation time.
The top bar, you have show taskbar display settings of the
Zoom.
No.
The screen that you're sharing, Navin. If you look at the very top.
Okay.
Is display settings in the middle.
Oh, I'm sorry. Could we just continue like?
It's okay. We can work. We can work.
Is that showing? Okay, I'm sorry about that.
Yeah, you're good to go.
Please bear with me since we don't have a lot of time. Right. So the proposal is adding FP8 formats to ONNX, the interchange format specifically. And I've seen that there is the pull request somebody raised on ONNX asking for similar requests, similar data types and operations. So it's going to be somewhat similar with a little more context added in and some additional operations and that we ourselves have seen in our testing. So this is a snapshot of the two formats that we wanted to add, E5M2, E4M3. One key difference that both of them follow sort of IEEE standard in terms of the exponent bias and the rest of the exponent matrix encoding, the binary format. The one key difference being that E4M3 does not support infinity. There is one single code, which is all ones with a sign bit, that's used to represent any error, either NaN or infinity. And overflows will be treated as NaN for E4M3. For E5M2, it's fully compliant with IEEE sort of definition. It's IEEE-like. That's the key difference. Those are the two formats, and both of them support saturation modes and overflow. Overflow on E4M3 results in a NAND. So that's the basic definition of the format and how the binary bits are used. Then we studied these formats for a while before they got into our roadmap, both for training and inference. I wanted to lead the discussion with some of the data so that we know what we found, what's interesting and useful in terms of the operations. So on the left side, we have computer vision models. We worked with some 25 odd models. These.
And saying maybe we're still on the introduction page.
Does it move now?
No, not for me.
Not for me either.
I'm sorry. This is
No.
If you want to get out of projection mode, maybe.
Yeah, probably that's a better idea. Do you see it now?
Yeah.
Yes.
Yes.
Okay. Let me clean this up a little so you get. Right. So on the left, now that you see, we worked with some 25 odd models, which are not entirely randomly selected, but which basically included vision models, which includes vision transformer, and all the convolution models, including some with the smaller, big, all sorts of different mix of models to have like a proper representation of computer vision workloads. On the right side, we have some 100 plus workloads with different data sets, mostly transformer-based NLP workloads. Translation, question answer, all sorts of different tasks have been studied. So all these models are pre-trained at a higher precision, and basically the task we wanted to do is quantize them directly and see how many of them can meet the accuracy requirements and how much of the workload can be converted to FP8. And basically, these are the stats on average across different data types. As you can see, the error for E5M2 is quite large. But E4M3 dynamic versus static, there isn't much difference, but there are few workloads that do better in terms of accuracy if we use dynamic. So we think this is one important aspect to support dynamic quantization along with static. Similarly, you can see the same thing playing out here. There's no discernible difference per se, but workload to workload, there are some workloads which do better with dynamic quantization. Compared to INT8, both FP8 formats do quite well in terms of meeting accuracy, and also the number of workloads that pass the threshold. So it's nearly 90+% for E4M3 and both with the dynamic and static quantization. On this side, we typically need dynamic quantization to get 100% pass rate for INT8 on the computer vision side, whereas we don't need that for here. You can consistently see FP8 doing better. So we studied all these aspects of what's needed in terms of quantization ops. And the next slide basically talks about the requirements that we extracted from that. Cast operations, FP16 to FP8 or FP32 to FP8. The default mode for inference, we use saturation. So the saturation is basically if the incoming value is larger than the FP8 max value, then you would saturate. Otherwise, if the incoming values are already infinity or NaN, we maintain that. We don't want to change that. In some places, I've seen people saturating these values too, but that's not the behavior of the hardware that we are designing. A non-saturation mode, again, these are passed through, and the value, if the value is more than max, this is IEEE behavior. For E5M2, it would produce plus or minus infinity. E4M3 produces NaN. That's the cast operation. Quantized linear and dynamic quantize, both operations would need. We saw that 0 point does help, although it's not a requirement for most NLP models. For CV models, we've seen specifically 0 point helping. So we want to support both 0 and 0 point and scale for these operations. Saturation rules again apply as defined before in the cast operation. For dequantize also, again, same thing. We use the 0 point and scale to do the dequantization. Then linear matmulls and convolutions. Basically, we want these defined so that we can plug in the high performance versions, because we can do quite a few optimizations when we know what scaling factor and offset to use. We can operate from the cache, and compared to compiler fused graph, these operations are quite fast, really fast. So we need that. These are fused operations too, and we also want hybrid operations to be supported. I don't have fully conclusive data yet on this, but we've seen that some workloads for inference. Training, it's a no-brainer. We definitely need this, but for inference also, we've seen some workloads do better in terms of accuracy when we use the mixed operations. And typically for inference, for inputs, it's E5M2, or for weights, E4M3. This is a combination that works well. For training, we need both combinations, and rest of them are basically uniform, non-hybrid operations. So there are quite a few others element-wise, and we will get to them when we have, maybe in the future, when we probably have another proposal. But for now, this is all I have.
Naveen, can you go to slide 2?
Yeah.
So one question I have is that how do we really express these two flavors of FP8 at a model level?
Right. So that's a good question. So you're basically looking at 8 bits of data. Is that what you're asking?
Yeah. So, we get a model, like how do we really express at a model, what format it is of the two?
So for ONNX, I'm not quite sure how the metadata is managed, but for PyTorch and TensorFlow, there was discussion to add metadata to identify which format, binary format this is, how to interpret the bits, basically. A similar thing could be used for ONNX. I'm not quite familiar with the system.
In the current proposal, they are distinct types, so the type distinguishes them.
Makes sense. And my other question would be, is the proposal that we support both of them because both of them have value? Because this would also increase costs for vendors to support. It's not as if we're adding one data type, then we're adding two data types then. Right? You need numerics to be essentially respected all along. And that may increase costs for all of them. So is your recommendation to support both? Do we have the reasoning for them?
So if you want to train, you need both, definitely. For inference, it's optional to do E5M2, but we've seen that, like I said, we've seen that hybrid operations help with accuracy, and even pure E5M2 also does better for certain layers, like layer norm. For instance, layer norm has a lot of outliers, which can't be not easily handled by E4M3. E4M3 still has a limited range. So it goes up to 448. So we've seen E5M2 do better in some cases. So I would see use cases where some parts of the network use E5M2 and others use E4M3. For instance, all the memory operations like layer norm, element-wise operations could potentially use E5M2, and all the matmls and compute operators could use E4M3. So I think both are needed if you're doing anything with FP8, definitely. Well, actually, there is a third one which Amazon is supporting on their Inferentia. That's E3M4, which is not widely supported. We don't really see the value of that beyond these two, but these two are definitely required.
Yeah, that's my point. I mean, can you exclude any other vendors coming up with a different representation? And also, that may be more a question for the standard and for Rama. But are they really mandatory? Because I mean, different hardware are going to, by definition, support different types. While we can all rely on FP32 and FP64 to be implemented for most machines, that's maybe not the case for those types.
Right. So in terms of interoperability or even the exchange formats, there should be, Onyx, I see that as an interchange format. I mean, you could define an agnostic intermediate format in Onyx, and which can do conversions to both, or 3 or 4 variations of FP8, for instance. What we are proposing here is this is what is supported currently by ARM, Intel, and NVIDIA, so that majority of the upcoming hardware in terms of volumes would have this format readily there available. But you could always add more binary formats, different ways of interpreting the same 8 bits.
And your recommendation is to have it defined at a operator level, seems like, right? Not at a
Yes
session or model level. Makes sense. So you could have...
And you could have model converters. I may sound ignorant because I don't really know exactly how Onyx works, but the way I understood the Onyx to be is that there is an intermediate format which is interchangeable between platforms, not necessarily tightly coupled with the implementation, right? I mean, I understand that the format itself, the binary, how the bits, the binary format has to be consistent across the platforms. When it comes to FP8, we don't have that agreement yet. So until then, you have to keep adding new types. Just like there are 2 with just 8 bits of data, there will be more of such. So I guess there's no going around that. There have to be mechanisms to do the model conversions between them.
Makes sense.
So one suggestion, I mean, so as you mentioned earlier, Xavier already has a PR in Onyx that we would like to merge soon. So if you can take a look and provide any feedback, I think that would be helpful.
Absolutely, yeah.
So specifically, I guess a couple of things. So for example, the points you mentioned in slide 3, I hope the spec in the PR is consistent with, sorry, not this,
yes.
Not this, the other one, I think.
This one? Right, yeah.
Well,
the spec is consistent with this format.
Yeah, this, and you also had a slide about saturation and
yes. All of that is consistent with the implementation. That
right. But I just want to make sure that the PR and the spec are consistent with this. And I guess, so if you, if you have any input in that regard, I guess that would be useful. For example, at least one small distinction I do see is, if I remember right, the PR said required 0 point to be 0 for quantize, dequantize. And if you think having a non-zero 0 point is useful, maybe it's worth mentioning.
Yes, maybe absolutely, yeah.
And one of the details about the PR is about saturation. Somebody wanted to convert infinity into max value instead of NaN. If you have a strong case against that, could you respond to the PR too?
Yeah, I can. So convert infinity to NaN. I'm not sure if that is. I mean, semantically, how is that going to help? There is an overflow or an error in the incoming data, the model. So it makes no sense to mask that when you're doing the cast operation or quantize operation. So you'd want to pass it along and propagate that error so that you'd error out and come out to that, right? Otherwise, how do you even debug these issues? If something is raised, let's say your convolution produced a NaN for some reason, let's say, and then, or maybe bit errors or runtime errors, right? Something is producing an infinity and you're going to saturate it every time and you would not see that error. In a real-time system, that would be disastrous. So we want to propagate the errors when they pop up. But when there are no errors, then you saturate.
Okay.
Yeah, but yeah, I think, right. Yeah, anyway, yeah.
Can you go to the next one, slide 2, Naveen, real quickly?
Yes, I've covered this already.
So the accumulations you want in FP32 or FP16.
Right, the hardware supports both. Some hardware supports both. Some hardware only supports FP32, but the operations could be defined either way. The output could be this, or output could basically include. It could just produce FP16, which includes the down conversion internally. So yeah, bfloat 16 is currently not supported, so I haven't added that. I'm not sure if there is some hardware that requires that, but these are the two that are currently defined in the spec, that common spec that we published, and would be supported in the hardware.
Yeah, I think in the PR, maybe there is bfloat 16 support there too. I guess that's another aspect that needs to be looked into. For in the context of FP 8, I think we should. Rama, would you think that we need to be explicit about it being 16 or 32, or it can be open?
Sorry, I mean the operators. You mean extending the operator to
the output? The output of the operator. Do we need to be explicit about it being 16 or 32, or is it okay?
Well, if we want to support both, I think we should just have an attribute which specifies the desired output type. And
makes sense. Makes sense. Cool. So I guess in the interest of time, I think we are running a little behind schedule too. If there are no other questions, I would want to invite Arnab, if you could maybe.
Thank you, guys.
Yeah, thank you, and thank you so much, Naveen. Thank you for your inputs. I think this is going to be a very useful proposal for ONNX and its evolution.
Yeah, sure. Let me just. Okay, I think in the invitation that I got, it said that hybrid FP8 and the proposal for multi-added attention as an operator. So I just heard from Alessandro Palla that he presented the MHA last week. So I don't think I need to go over that again, right? Sort of. I don't know.
Yeah, you can move on. Let's just focus on what additional things that you have.
Yeah, sure. So this won't take too much time given Naveen went first, right? So I think the main thing here is just to point out some of the complexities and ambiguities in supporting FP8 with other floating point stuff, and how do we want it to be specified so as to remove some of those complexities. So quickly going over some of the accelerators that we have in Intel. They support kind of a combination of different floating point types, right? So we have support for FP16 and BF16, as well as support we will be having support for FP8, like both. And in this case, just to get the terminologies right, for this case, we are kind of saying E4M3, which kind of Naveen presented as HF8, and E5M2 as BF8, right? Just to get the terminologies right in this case. And we support a cross of them, right? That means that we can have, for MATMUL as well as element-wise operations, we can have a combination of either FP8 and FP16. Like it can be an FP8 combination with with FP16, BF8 with FP8, BF8 with BF16, all the combinations, right? Right now we have, right? Now when we do inherently FP8 with an FP8 kind of a MATMUL, we inherently support operations in the FP8 domain. But when we do an operation where an FP8 tensor is getting kind of multiplied or convoluted with kind of an FP16 or a BF16 tensor, so the way it is done now is that we upscale the FP8 to a BF16 or an FP16 and then do the operation itself, right? And the same goes for element-wise, right? Whenever you have a FP8 tensor and a FP16 tensor, first you kind of upscale it to that corresponding FP16 or BF16 tensor and then do the element-wise operations inside, right? And as Naveen said, I think for most of our stuff, the accumulation is done right now in FP32 for all of our stuff, right? Now, when we support this FP8, there is usually an added complexity, and the complexity comes from the limited dynamic range that is kind of supported by HF8, right? And the way we kind of get over this complexity is by adding kind of a scaling factor, right? And as it's done for Int8 also, right? So we have per tensor scaling factors which needs to be applied to this FP8 tensors before you do the kind of the MATMUL element-wise multiplication or element-wise add in this case, right? And I think more on that can be found in the white paper that Naveen has published, like the Intel ARM and NVIDIA white paper that we have, right? Now with the scale factor, from a hardware accelerator point of view, for operations such as convolution and element-wise multiplication, it becomes easy for us to apply this scale factor. Quite simply is because we have something called a post-processing engine where you can combine the two scale factors for tensor A and tensor B and apply it at the end, right? But the place where it becomes a bit complicated is when we have these scale factors for element-wise add and subtract, right? The reason why it is the case is that you have to apply the element-wise add. So you have tensor A and tensor B, and say you are applying scale factors of alpha and beta to them, and say they usually are in FP16 or BF16 format. So you have to do alpha A plus beta B, right? And in this case, so the way it happens is that you mention the scale factor in a FP16 or a BF16 format, and your inherent FP8 tensor remains in FP8 and BF8, right? So there is this mishmash of kind of formats happening which we need to take care of, right? And for that, we had to apply a lot of rules within the hardware, right? So for example, when we have element-wise addition and subtraction for two FP8 tensors, the way we do it is that so we say both of them are of the same format, right? BF8 and HF8, right? And your scale factors are given either in BF16 and FP16. So we have to upscale them to the corresponding FP16 or BF16 format before the addition and the subtraction takes place, right? The complexity comes now if your two tensors are of different FP8 formats, right? One of them is BF8 and one of them is HF8. In that case, you have to see the scale factor, whether it's in BF16 or FP16 format, upscale it to that correct kind of like the 16-bit format, and then do the scaling as well as the element-wise addition and subtraction on top of that, right? And the same thing happens because we kind of support kind of a mixture of element-wise addition between an FP8 tensor and BF16 tensor. This is a bit straightforward because the FP8 tensor is kind of is going to get upscaled to that corresponding FP16 or BF16 format, and we expect that the scale factor is of the same format as that of the BF16 FP16 16-bit format that we support. But that right now happens within the hardware itself, right? So one of the suggestions, I know Naveen kind of presented a support for linear conv, quantized linear conv and MACML, but in the long run, if we are thinking of supporting L2WISE also as inherently FP8 because of to get kind of the memory savings that we have, I think the suggestion here is that to avoid any complexity, we may want to dequantize, like before an L2WISE add and subtract, we may want to dequantize the activations to the correct FP16, BF16 format, right? Before kind of going ahead and doing these element-wise operations, so that we don't have to kind of take care of this upscaling within the hardware accelerator itself and kind of take care of these different formats or mishmash of formats that we have inside. Yeah. So yeah, that's basically the thing that I wanted to kind of express here. Sort of. Yeah.
Makes sense. Thank you so much, Arnab. Then thank you for your contribution too.
Sure.
To me, it makes sense, and absolutely. But Rama, do you have any thoughts around this, or how would you like this to be taken further? If there are more questions, in the interest of time, maybe we want to take it offline. But if you think it is something quick, then we can cover.
Yeah, I mean, if you don't have time, I guess we can move on. I mean, I was not completely clear what the exact constraints are, but yeah, when we get around to extending the support for FP8 to other ops, yeah, this is something we should take into consideration. But yeah.
Right. So Arnab, essentially, in the first proposal, in the first go, things are relatively simpler and we are not mixing the two. And essentially what we are saying is maybe in the next phase of it and the next revision of it, maybe some of these things should be covered. And I think your suggestion is very important in that context too.
Yeah, right now, in fact, I think we don't even have element-wise operations like addition on FP8. But if I understand right, supporting it on the same FP8 format is okay, right? Yeah. It's only when you mix them,
yes,
you have to. Okay, all right.
So can we just settle, like in the beginning, we can just say in the first drop, we're not mixing them, right? The flavors couldn't be mixed in the element-wise.
Yeah, it can be mixed. It's like we support at least the mixture, right? Okay. It's just that we then upscale it to the common kind of 16-bit format, right now. So either both of them gets upscaled to FP16 or BF16, right? So that's why.
So how do we, in the first PR right now, do we allow the mixing or not?
So in the current PR, actually, these ops are not even supported. So it's.
So if I may say, I think the trick is to basically, this is for a specific vendor with specific constraint for a specific hardware. And I think the trick is to find an exchange format, since we are at a standard level, something that makes sense and that is generic enough so that it's compatible with various different vendors that may have slightly different combination of those things. And at the same time, that doesn't preclude high performance when you go running on a specific hardware. So that's, I think, the balancing act that we should aim for. Not to be too specific, but at the same time, allowing good performance on the models that we targeting for specific hardware.
Good point, Alex. So I guess what I would suggest, Arnab, is like maybe you can add these comments to the existing PR.
Sure.
And let's discuss it further there too, right? I don't know if we'll be able to cover all of it today.
Sure.
We have like a few other proposals to cover.
Sure,
okay? Sir. Does that sound good? Okay.
Yeah.
With that said, Murli Ambati, are you there? All right, I didn't hear a yes. Arnab, can you check if Murli is going to present?
Yeah, I can.
All right, so the next presenter we have is Lucas Fisher from Data Lab. He is discussing about quantized linear and dequantized to have another bit, adding bit parameter to it for hardware compatibility. Lucas, are you here?
Hey, he's here, and you should be able to present. We don't hear you though.
it better now?
We can hear you now.
Perfect. So nice to meet you all. I'm going to share my screen. Tell me if you can see it. Post disable attendee screen sharing at the moment.
You should be a host now. Sorry, I thought I did it, but
indeed, no worries.
It works. We see your screen. You can go ahead.
You are muted again, Lucas.
You're muted.
I don't know why, but as soon as I'm starting to share my screen, it disconnects my mic, which is quite weird.
And it is muted.
Is it better now? Now,
yes,
yeah, perfect.
Yes.
Okay, sorry. So feel free to cut me. I cannot see you all, so feel free to ask any question. So just to present, we are a bit smaller than Intel that did all the other presentation today. So we are Dataka Lab. I'm the CTO of the company. And basically, we are a neural network compression company working on quantization and other kind of methods. And we have been pushing quantization to the extreme and to low bit quantization. And especially on low power device as RISC-V or microcontroller. And that's in that idea that we wanted to present and add something to ONNX, because we are a huge fan of ONNX, and our product in quantization and printing is built around ONNX. So what I'm going to discuss about is something actually simple to understand, is that there is more and more hardware that support low bit quantization. So we are working with a couple companies, and some of them working with RISC-V device support ternary to int8 quantization for the weights. Untether AI, which is a big startup working on edge kind of NPU, has support for int4 to int8, and ST Microelectronics support binary and int8 quantization. So they support, all of them support ONNX. But what we found out is that as of today, in the ONNX format, you can only express int8 quantization. You don't have a way to express if you want to go to low bit quantization. And for specific use case, such as sound analysis, for example, for really tiny device, for voice enhancement and stuff like that, you might want to do int2 quantization or int3 quantization or whatever. And you want to be able to communicate between your quantization scheme to the hardware that will be putting that onto the device. And actually, after looking closely, and there's actually an MR that already discussed the idea I'm presenting today. It's actually something that was done in August last year. And actually what they presented and asked was to add some type to the protobuf in order to store low bit representation of the weights in the proto. And after some discussion based on what was said there, it would be seen that it would be a big merge request and big change into ONNX. So what I'm presenting here today is something that's actually someone from the ONNX community already presented, was to add the bit width parameter into the QDQ operators explicitly, in order to have a clear understanding of how it should be run. And that should be helpful into going from the quantization scheme to the device. And so just to explain to you why I try to stay high level, I have an idea about how to add that to ONNX, that why is it I think a good idea is it's going to be simple to have a backward compatibility with what's already available. The default would be int8 as it is today. It will help in making ONNX a better framework for tiny edge MCU FPGA RISC-V. I'm sure you are all, some of you might be familiar with QONNX, that I think is pushed by some HLS or NZLinks, and but the format is a bit different. So having that into NNX could be helpful. It's not a massive change, so it will not change anything major, but it will help in improving the experience of quantization. Compare what can be available into other frameworks such as TF-Lite, because you will have access to lower bit quantization, and it will make a bigger impact for NNX and how it is deployed today. So I went fast. The slides are simple, but I wanted to discuss with all of you.
Thank you for the velocity, Lucas. So the quick question for you is, did you do any study on any other framework, like how are they expressing in 4 and 2? And do you have any data around it?
So based on what I've seen, like there is a couple of frameworks. So TF-Lite, you cannot do anything when you actually want to. It's difficult to go into that path. But if you go for QKeras, for example, they have that bit width parameters. In QNNX, they also have that bit width parameters that is available and can be shared in 2 ways inside the convolution, from what I remember, or inside another file where you share some information. And lastly, there is I was discussing about QKeras, QNNX, and the last one is NNCF by Intel, I think, where they actually expressed that in some way in the model. I haven't been able to dig deeper on that end, but it's not in the semantic of the model, and it's not in the NNX format. And what I like about the idea of adding that bit width to the NNX format is that it will be a standalone format where you add what's necessary, and you can share that between different hardware manufacturers, and will make what makes sense for NNX, which is the exchange, simpler.
I have other questions, but I'll let the rest of the floor to others. Rama, if you have other questions.
No, nothing from me.
Okay. So Lucas, are you proposing this bit width just for integer types, or is it for floats too? Because we just heard a proposal in float that there are other flavors to it. Is it just int then?
So in our case, what I want, like I saw the other proposal, and I would be fine to discuss with the other person working on FP8 to discuss how we can address those 2 problems at the same time into something bigger. In my case, I'm more talking about adding the bit width directly for integer, and to see at the same time if we how we can make it work for different floating point representation as well. But it's in the proposal I'm giving today. It's more about integer, like binary, ternary, neural networks, stuff like that.
Okay, so your proposal covers both floating and integer types. So like FP4, like floating point 4-bit, if somebody wants to do, I don't know. Yeah.
So in the case, it's more integer, so it covers integer, but we could adapt that for floating point as well. But I'm not super, I would need to discuss with the person pushing FP8 such stuff or FP4 on who wants to, if it makes sense, to see how we can address those 2 problems into the same MR. But right now I'm just talking about integer quantization and low bit integer quantization. But could be added and could be modified a bit to discuss with the right person. Does that make sense?
That sounds great. Any other questions on the bridge?
Yeah, one question is that. So the data types that you are interested in are ternary and binary, or you also mentioned 3 bits in between. Is that?
So I would like to have something that works independently, like something general, like on the clamp that could work even for int3, because one of the partner I was referring to actually support int3, which is and they have ways to improve and get better results with int3. So it's not the case for every hardware, but for them it makes sense. So I would say something that is general and agnostic, and not only binary or ternary, but more a wider range of possibilities all the way from int A to binary.
Makes sense. I think, Lucas, thank you for your contribution. This is, I think, very useful. Ternary operators are taking a lot of attention. What I would suggest is let's just follow up on GitHub and solicit feedback from the community. And I think Rama and Mikhail should be able to take it further on the conversation. Okay. With that said, I would now want to invite, do we have Peter or Alexander or Thomas here too?
Yes. Hi. So I'm Peter.
Okay. Hey, Peter.
Let me share my screen.
Know if it works.
Okay.
Yes, it
Is
works. Yep.
the presentation coming through? Okay. So I'll just go ahead and that's okay.
Yes.
This will be pretty short. So I'm also with Intel. I'm in a team in the corporate strategy office in Intel. Yeah, just wanted to mention we've been working with Onyx and using Onyx, on a technical level. But me and my team were new to this forum and kind of the Onyx standardization activity as a whole. So please bear with me if I'm missing, major concepts. But essentially, what we'd like to do is to use Onyx essentially as intermediate file format for fully quantized models, fully int quantized models. So the models could be produced by the neural compressor or other tools that produce quantized models, and would be consumed by a graph compiler or some inference tool chain for further lowering and execution, and we're in the domain of embedded computer vision. So again, that's why we're interested in kind of this pipeline of fully int 8 models and inference. So as I mentioned, we've been working with Onyx, and right now we see in the Onyx standard itself, there's a limited set of QOPs. So we started working with QOPs. We see there's QLinear conv and QLinear matmul, and then the quantized linear, dequantized linear, representing actually quantization and dequantization. Then we see in the Onyx runtime contrib library, there's a wider set of QOPs. So QLinear, concat, average pool. There is an add, but not a sub. As far as we saw, we see a mul, but not a div. And so, yeah, so partly we're wondering why these are not part of the standard itself, and why there's not sort of a more complete set of QOPs. And again, we're kind of new to this standardization effort, so we may be missing what are the underlying reasons here. But basically, our recommendation or suggestion would be to adopt a wider set of QOPs, so that we can basically express the model just completely with QOPs. We're not necessarily proposing QOPs for everything in all operators in Onyx, but we see basically a kind of a core subset, if you will, that we've been working with, and maybe there's not a hard boundary, but basically this is kind of the list that we're thinking about. So concat, add, sub, mul, div, as well as average pool, and global average pool. yeah, so that basically is a suggestion for the standard itself, and then yeah, whatever else needs to be done in the library or other areas to kind of enable this more robust support for QOps to enable this end to end. For again, our application is for embedded computer vision, and basically the type of models, maybe I can call it basic or compact models. Are not proposing to do this for every kind of model out there, but that's it.
Peter, which domain are these ops more prevalent in? Is it just computer vision, or you see it as others too?
Embedded computer vision, yeah.
Okay. Yeah, I think I don't have any other questions. Raman, do you have any?
So I guess one direction that Onyx has been moving towards is having this QDQ approach where we use quantize and dequantize, but don't extend other ops to explicitly create quantized versions of other ops. So we rely on actually the composition to express the computation, allowing backends that have support for quantized implementation to actually identify a subgraph that involves quantized computation. So you can replace it by a call to a specific quantized op implementation. So do you think that approach is not sufficient or has any limitations, I guess? So yeah.
Yeah, so I'm aware of kind of the QDQ approach. We in our project, we have a preference for QOps, and with QDQ, probably, I mean, I don't fully understand the situation on my side. I think in the sense that it seems with QDQ or in many existing implementations that you kind of get this mixed approach, right, where you have some QOps and as well as QDQ for handling a lot of other things, which may be a flexible kind of approach, if I understand it correctly. We just we have a preference for doing things with QOps end to end. Just it makes the model sort of simpler and streamlines the pipeline. But yeah, having said that, I mean, I it's not something that is impossible to do either. But hope that makes sense.
Yeah, I mean, I guess, I mean, one possibility is to try to define QOps as functions in terms of quantize, dequantize, and the underlying primitive ops. And that way, the set of primitive ops in Onyx doesn't keep increasing. I guess that. I guess what we could try to do is try to see all these QOps can be defined as functions in terms of quantize, dequantize, and the other primitive ops.
Okay. Yeah. Thank you for that suggestion. Yeah, I understand that maybe there is some hesitance to kind of proliferate or proliferate every type into quantized versions or other versions. Is there, if I could just ask, I guess, is the reason that convolution and matmul are there is just because they are the most critical in terms of execution resources and so on? Is that why Onyx does have, let's say, those all QOps?
I think it's more historically, I guess those QOps were added initially before shifting to using quantize and dequantize as a way to avoid proliferating the ops. So yeah, it's more a historic evolution, I guess.
Yeah, I think at the time when we added QLinear on and MACML, because we wanted to keep it lesser number of ops that could be quantized and keep the hardware complexity and software support simpler. So we started off with those two. But then we realized that there are other ops, other places which need to be quantized, and then maybe a QDQ operator will also make sense. Mm-hmm. So that's why I think both exist.
We could consider making a whole family of QOps functions, and if that were possible, we could even make the existing QOps functions as well, although we'd have to think through the implications of that.
Yeah. I think that's...
If I look at the convolution... If I look at the convolution...
The existing ones, sorry, Alex, real quickly. Changing the existing ones may have more implications to it, but I think it's quite prevalent now, right? Go ahead, Alex. You were saying something?
Yeah. If I look at the convolution, I mean, the quantized linear convolution has extra parameter. So I think the question is how they would be embedded. And I do think that we have either the approach to have separate operation that specifies something on the output that can then be integrated, that works well with a compiler approach or something else, that's trade-offs to be looked into.
Exactly. Yeah, makes sense. I think what I heard from Rama is like maybe a possible approach is to add these, the new ones that Peter is proposing to be like functions. And if that is something that you would like to pursue, then I guess you can follow up offline on it, Peter. Does that make sense?
Yeah. Thank you. And I think also moving the existing Q linear ops to functions does make sense because it fits with some of the earlier goals of the operations work group to try to simplify the core ops and move some of them to functions. I think there's been they've been slow about doing that, but it does fit with some of their stated goals.
Okay. Good.
Yeah, I'd like to understand more about what exactly would need to be done, but we can discuss it offline. Yeah. Thanks.
Yep. Any other comments for Peter? If not, I think we are almost at time. I know we missed one from Murli. Murli, are you here?
Yeah, I just need a minute. Mine is very simple.
You should have already access to presentation.
Yeah. So can I go ahead?
Yes, please.
Okay. So what? Can you see me? So the request is for the quantized, dequantized linear ops. I also just give me 1 minute. So the request is to support float 16. For example, quantize where we are going from float to int. Right now, the on expects the input to be float 32 if it's float, but not float 16. So we want to add that. So in this case, what I'm showing is the spec. This is a T1. This is the tensor to be quantized in the spec. It is either float or int32. We want to add float 16. Similarly, for the dequantize where we are going from into float.
Are you sharing the right
seeing
screen?
an email.
What are you seeing? Sorry.
Yeah, we're seeing my email to you.
Oh, sorry.
I'm glad.
Okay, let me see. Can you see it now? Well, the Word document. Yeah, so two things. One for quantize, where we are going from float to int. The current ONNX spec says the float should be, if you hear what I'm saying, the T1. T1 is either float or int32. The request is to add float 16. Similarly, for dequantize, where you're going from int to float, the output is float. Want to add, in addition to the float, add float 16. So that's the advantage. So the key point is like a lot of like, for example, our accelerator we have dedicated int 8 and FP16 support, and so there is no need for us to go from FP32 to int. Yeah, we have dedicated support from FP16 to int and into FP16, and we want to have the same in the ONNX spec. And if you see like the Microsoft that contrib operators, even in that the quantize, linear, and dequantize, they do have support for float 16. Yeah, and we want to reflect that in the ONNX op spec too. Yeah. Yeah, it's just simple.
Basically adds float 16 support to be more comprehensive in ONNX.
Yeah.
Rama, any thoughts from you? I know we're out of time, but how would you like to dispose this request?
Yes, well, I didn't follow the details. I mean, we could potentially, I guess, discuss this in the ONNX repo as a discussion or issue. I mean, some of these things, I mean, given that there's not enough time to really understand
So, okay, so
fully,
so the main point is like for quantize and dequantize, where we go to float to int or into float, the request is in the float add FP16 data type 2. Yeah, that's in summary, that's the request.
Okay, yeah. I mean, yeah. I think that should be reasonable and easy, I guess, just extending the set of types to support FP16.
Yeah. Okay, thanks.
So Ram, I can add to this, but I think basically the way the committee works is like you can always have a pull request or issues that you open on GitHub, and a lot of the discussions happen there, and that would be for many of those proposals probably the ideal way to do it. And I think we also, if you feel like there's a need to further discussion, also schedule a time slot in one of the upcoming operator presentation. Which I typically once a month. And all this is often on a Slack. You can also discuss things directly on a ONNX Slack.
Okay, thanks.
Awesome. I guess we are more or less covered. Today was, I think, quite a productive and exciting day. We had a lot of interesting proposals. int 8, FP8, low bit precision, and now FP16. So it seems ONNX has a lot of energy behind it and a lot of innovation happening. So thank you everyone for joining, taking the time. We really value all your contributions, and I look forward to our next session. Next session will again be chaired by Alex, same times next week. Okay, and we'll follow up on the GitHub with the issues and all that stuff, the rest of the things. And I believe Alex would also be uploading your presentations at the right locations. Okay.
Thanks a lot, everyone.
Okay. Thank you, guys.
Thank you.
Thanks for the presentation. Bye-bye.
Thanks. Bye.